Assalamu alaikum. Uh, Today we are going to talk about moments, and let's see what's happening here. We have a Pelton wheel here. You might have heard of it before. This is a Pelton wheel, and this is a simple arrangement that is made to utilize the potential energy of water to generate electricity. So what is meant by that is that we from a certain height passes a fluid through a penstock and a nozzle arrangement, and this fluid hits the buckets and rotates this wheel like this. So we can use this rotation to generate electricity, and that is the function of a Pelton wheel. So now what is concerning us is the force that is applied on these buckets. So the force the water is applying on these buckets. This force is applied at a certain distance from this point of rotation, or if we call this point O, we can say that O is our axis of rotation, and this force is applied at a certain distance from this axis. If we call this distance R, R is basically for radius. So what is happening here is a force is being applied around a certain axis at a distance r. So we can write it like this, that moment you can relate to this equation, moment is equal to r cross f. So here a force is being applied at a distance r from axis of rotation O. So what happens? It will generate a moment. So this is what concerns us in this portion of our fluid kinematics, that we will talk about the moment that will be generated by our momentum of fluid. That if a fluid is moving, so what moment will it generate if it is passed through this sort of arrangement, like a Pelton wheel or a garden sprinkler that we will see in the coming slides. So what is the moment that is being generated, and how will it be generated, and what will happen to this moment of momentum when we write it in the Reynolds transport theorem? What will be its situation in that case? So here again we are passing a liquid through a certain height through a penstock and nozzle arrangement, and it is hitting these buckets on this Pelton wheel, and it is rotating this Pelton wheel, and this Pelton wheel is helping us to generate electricity. So we apply this moment to overcome a certain amount of inertia in this shaft of this wheel. This is the shaft of this wheel, and this shaft has a certain inertia. And what is inertia? Is a body's ability to do nothing. Like if it is at rest, it will remain at rest, or if it is moving with a uniform velocity, it will move with a uniform velocity. So here this moment right here that we have applied with the help of this fluid and at a certain distance r from this axis of rotation, this moment will overcome this inertia, and in this case this inertia is called moment of inertia. So what we will do is we will apply moment with the help of our momentum that is being generated by this fluid, and we will try to overcome this moment of inertia, and this moment of inertia is also known as torque. So remember when we had a discussion that what is the difference between torque and moment. So they are basically the same thing, but one is applied, the moment is applied, and torque is the force or the moment that we want to overcome from this applied moment. Torque is basically the force that we want to or the load will be the appropriate term to show that the load we want to overcome to rotate this Pelton wheel. So moment is applied and torque is reactionary. So we will like to overcome this reaction force to rotate our Pelton wheel. So this is what we are going to do. We are going to take the moment of our momentum. In the last portion, we took our extensive property as momentum and we equated to summation of all the forces. So what we are going to do now is we are going to apply it with the appropriate distance that this momentum will make with a certain axis, and ultimately the force is 2. So we will be generating moment for our momentum, and this is what we will talk about, moment of momentum. Here our extensive properties will now look like this, and this is how we are going to put them in our Reynolds transport theorem. So these Pelton wheel and other turbines like this and pumps are called turbo machineries. Turbo machineries because these machineries are used to generate electricity or transport fluid from one point to another. Like if we say Pelton wheel, Francis turbine, Kaplan turbine, they are used to use the potential energy of water and convert that into electricity. And in case of pumps, we use the electrical energy to do some work on the fluid and transport a fluid from a certain point from ground to a certain height h on the roof, and that is in the case of pumps when our machine is doing work on some fluid, and in case of turbines our fluid is doing some work on this machine. So these are all called turbo machineries. So now let's move on to the next slide and put these terms, our moment of momentum terms, and write them for our Reynolds transport theorem and see how it looks like. Now let's write some equations for our moment of momentum and see how it looks like. So this was the previous equation that we wrote for our momentum. This is the Reynolds transport theorem that we wrote for our momentum term, that is the velocity and mass, velocity, mass and velocity and our mass flow rate. So this is how it looked like when we put our extensive property B is equal to mv. Now let's write this term, this left hand side of this equation, that is the total change in the extensive property of a system for a single particle, and equate it to the force that is being applied on a single particle. So this is again our momentum term, and that momentum is the force, the summation of forces for this particle that is equated to this term. We already know this, but to apply momentum we need to multiply a certain distance with these terms. So this is how this equation will now look like when we multiply a certain distance r with these terms. So we can get the moment for this momentum. This is also momentum. So now we are talking about moment of momentum terms, and as you can see, if this is our section of fluid through which the fluid is flowing like this, like fluid is coming out of this section, and if we take a perpendicular distance with its velocity, like this is the velocity of this fluid, and we take a perpendicular distance with this velocity r from a certain axis, that is our axis z, and we multiply these two terms, so we will get another perpendicular term, that is r cross v, that will be perpendicular to the both of these vectors. And this is what cross product does, that it gives us a vector that is perpendicular to both these vectors, or a perpendicular to a plane. If we draw a plane like this, so we will get a vector that is perpendicular to this plane, and this is the vector that is perpendicular to this plane, that is the r cross v vector that we will get by multiplying vector v, velocity, and r, the perpendicular distance to this velocity. Okay, so this is what we have done here too. We have multiplied the momentum terms with a distance r to get our moment of momentum. We are doing it for a single particle. We will integrate it later for the whole system. So to keep the distributive property in check, that is what we have done here. We will take the total change with respect to r first, and then we will take the total change with respect to the momentum first, and then we'll see how this left hand side of our equation, that is the total left hand side of our this equation, looks like, because we are now talking in terms of r cross v. So this is simple distribution, like we want to apply d by dt on r cross v. So this is simple distributive law. We will first do dr by dt cross v and these terms, that is the density and velocity, the volume, density, and the delta volume. So this terms equates out to be the mass, and plus now we will leave out our r and take the total change of our momentum, that is r cross d over dt v rho and delta volume. So this is the momentum term, and we are just applying the distributive law to keep our maths in check and see that we are doing things correctly according to the laws of mathematics. And here we have just applied the distributive law on r cross v, and what will happen here is that dr over dt, that is the change in system with respect to change in time. So what does this gives us? It will gives us velocity, because velocity is the change of distance with respect to time. So what will happen is that we will get here v cross v, and the cross product of the two same vectors will be equated to 0. So this term as a whole will be equated to 0, and from this distributive property we will get this term only. So this is what our left hand side of the equation will now look like. So let's move forward and see how they have written these equations, and this is what they will do, what I have described now. This is what dr over dt will look like. It will look like this. It will be equated to velocity because it is the change in distance with respect to time, and by equating this term to 0 we will get our left hand side of our Reynolds transport theorem like this. So this is our perpendicular distance through which this force is applied, and it will be equated to r cross v rho dv, rho delta v in this case, and that is the r, v, and mass. So what we are doing is that we are taking the moment of this momentum mv, and that is its momentum. So this is how our left hand side of our equation will now look like. Now we will integrate this term for our whole system, because this is what the change in system represents. Our left hand side of the Reynolds transport theorem represents the change in the overall system. So we will integrate this equation for our system now and write it on our Reynolds transport theorem. So let's do this. Now we will write our left hand side of our Reynolds transport theorem in terms of the system, and this is how it will look like. This is our left hand side of our Reynolds transport theorem, and now the total change inside the system is with respect to R cross V, that is our R and V and mass. So now we are talking about the total change in the moment of momentum inside the system and equating it to these terms, like the moment that needs to be overcome. What does this mean? Basically, the left hand side of our Reynolds transport theorem turns out to be the torque that we need to overcome in a certain turbo machinery to rotate that machine. So let's write these terms for to explain a little bit further that what do they mean. This is the time rate of change of momentum of the system, which is equal to the sum of external torques acting on the system. So these external torques is what prevents rotation. What does this mean? This means that if no force is applied on our let's say that Pelton wheel, if we say, let's suppose that no fluid is striking the buckets in our Pelton wheel, so what will happen? The Pelton wheel will ultimately be brought to rest. So what is bringing that rotational energy to zero? This is that external torques. These are the external torques that are already present in our system, that rotational inertia, and what we will do is we will try to overcome that rotational inertia and turn our turbo machinery so that we can generate some power. Now, writing these terms for our Reynolds transport theorem, this is how our Reynolds transport theorem for our moment of momentum will look like. Now this is for our moment of momentum. Now this is the left hand side of our Reynolds transport theorem, that is the time rate of change of momentum of the system. This is this term, which can also be equated to this, that we will do further, and that is equal to the time rate of change of momentum of the contents of the control volume, that if any moment of momentum is occurring inside the control volume, but we will mainly take steady state problems under our consideration, and these terms will be equated to zero under steady state. And then the net flow of the moment of momentum through the control surface. These are the control surfaces, and by control surfaces I mean my inlets and outlets. The inlet of my flow and the outlet of my flow is the control surface, and the net flow of the moment of momentum through the control surface. So this is what I have done to my Reynolds transport theorem. I have multiplied it with a simple term R. All the terms are multiplied now with a simple term R now, and this is what this R term, when applied by a certain momentum will generate a moment, and this is what we'll going to see further. So this left hand term that turns out to be the sum of the external torque, and I'm repeating again and again that we need to overcome this torque to rotate our body. We need to overcome this torque to rotate our body, and how will we overcome it? We will overcome it with the help of our terms on the right hand side, that is the momentum that is being generated in the control volume, and the net inflow and outflow of our fluid, and the momentum that it generates, and the moment that it will generate on these control surfaces. So this torque is the load that needs to be overcome by the fluid momentum to rotate the rotor in this case. So that left hand side, on that left hand side, whenever we will do a problem or an example, what we'll do is we will write those forces that are preventing this rotor from rotating. So those will be our torques. Those will be our torques, and they need to be overcome by this fluid momentum to rotate my rotor. Now let's take an example of our rotary sprinkler, that is the garden sprinkler that normally is used to water the garden. So this can be our rotary machine, in this case in which a fluid is being flowing in here and is coming out here. So what is happening is this sprinkler is rotating. So we can take this as our momentum problem, and we will like to write certain equations for this scenario now to see that how our Reynolds transport theorem will behave when we apply that equation on this scenario. So let's see and write our Reynolds transport theorem. This is how our Reynolds transport theorem will look like when we write it for the moment of momentum. This is our change inside the control volume due to the moment of momentum. We will consider this a steady state flow problem and will equate this to 0. What we will concern ourselves is the momentum that is generated by the fluid by going in and out through the control surfaces. There are two control surfaces. One is at this section, that is the section 2, that section. This is the section 2 that they are talking about, and the exit of this sprinkler through which the flow is getting out. So this is a disk type control volume that is being defined for this particular case. You can see the blue dashes, these dashes and these dashes. Overall they represent our control volume. This is the pictorial view and this is the top view of our particular case. This is the top view, and we will come to these velocities in a little while. We need to write equation for velocities as well, because in this case, or in case of every turbo machinery, what will happen is that inside the control volume, inside this control volume, our turbo machinery or any rotor of our turbo machinery will rotate. So then we have to assign certain velocities to differentiate between the velocity of the rotor, velocity of the rotor, the velocity of the water that is coming out, and what will be the reference points for these velocities. So this is what we are going to do in this slide. So again, coming back to the Reynolds transport theorem equation, this is our moment of momentum generated by the fluid coming in and out of this system, and the torque that is preventing the rotation. This will be equal to the torque, and this is the shaft torque. This is normally called the shaft torque. This is the torque that I was talking about in the previous slide, and we need to overcome this torque to rotate this rotor, and we will overcome this torque with the help of this portion of our Reynolds transport theorem, in which the fluid is going in and out, and it will generate a certain moment to overcome this shaft torque. So let's talk about the velocities that we will have in this scenario, and if our rotor is moving inside the control volume, what will be the velocities and how will we write an equation if we want to relate different velocities of the rotor or the water that is coming out of that rotor. So what we will do is we will define a control volume, that is my control volume. Again, this same control volume, the top view, and this control volume is fixed with the help of some other three-dimensional Cartesian coordinate system, that is my x, y and z. Its position is fixed with respect to this reference point. This control volume's position is fixed in space with respect to this Cartesian coordinate system. Okay, and we will have velocity of the water coming out with respect to this control volume. So these are the velocities that I am called v theta 2. These are the tangential velocities that are coming out of this portion of the sprinkler, that is V theta 2, and this is also V2, which is V theta 2 in this case. If I am seeing the velocity of the fluid with respect to this reference point, then I am going to represent the fluid velocity as my tangential velocity V theta 2. And why the tangential? Because we have three components here. One is the z-axis, one is this z-axis, my axis of rotation. This is the z-axis, which is my axis of rotation in this case. The other is my radius, and this is the radius that this velocity will make with this axis of rotation. So the other is r, and the third one is theta. This theta, this is the direction that my rotor will move along, this theta. This is the theta. So I have mainly three components. One is the z, the axis of rotation, the radius r that this axis of rotation makes with this theta, that is the r, and theta is the rotational direction in which this sprinkler will move, and any velocity that is tangential to this theta will be represented as v theta, that is again v theta. So this is my two velocities, that is coming out of this the fluid velocity that is coming out of these portions of the sprinkler, and similarly for these portion of this sprinkler if you want to specify them in the top view. So this is the velocity of this fluid, and its reference point is the same reference point that I have defined for this control volume, and this is the reference point for these velocities. Now my control volume is fixed, but inside that control volume my rotor is moving, my rotor is rotating. So now what will happen when I need to assign certain velocities with taking the reference point as my rotor? So that velocity will be let's say this is my rotor, and this arrowhead is representing the fluid that is coming out of this rotor, that is the fluid that is coming out of this rotor, and that velocity will be represented as W. So that W is the velocity with reference to these control surfaces, means for these velocities W2, as you can see here, they have shown this here W2. What will be the reference point for this velocity? For this velocity, the reference point is the control surface, and that control surface through which the fluid is coming out means this control surface. If I would change the color, this is the control surface through which the fluid is coming out, and this is the control surface through which the fluid is coming out. So if I am taking my reference as these control surfaces, and I want to measure a velocity of the fluid that is coming out of these control surfaces, and its reference point is this control surface, so I will represent the velocity of my fluid as W. So now we have two velocities. One was V theta 2, that was the tangential velocity of the fluid through some fixed reference point, and that reference point was the same reference point that was used to fix this control volume in space. So we call that velocity V theta 2, that is again our fluid velocity. And W2 is also our fluid velocity, but for that our reference point is our control surfaces through which the fluid is coming out. That is also our fluid velocity. So basically, what is the difference between these two? The difference is the reference point. For the v theta 2, we take the reference point as the reference point we took for our control volume to fix this in space, and for W2 we take the reference point as our control surfaces. So this is the main difference. And then we have a third velocity, and that third velocity is our velocity of our rotor, that omega sign. This is the angular velocity of our rotor. But we can, as you see, we have three velocities so far. In these three velocities, we have v theta 2, W2, and omega. These two velocities are linear velocities. These are linear velocities, and this is the angular velocity. And we have an expression to convert our angular velocity into linear velocity, and we will use that expression, and we will represent it as u is equal to r omega. Remember that r is this distance. R is this distance. That is my actually the moment arm. So if you multiply the moment arm with angular velocity, you get linear velocity for this rotor. So we want all the terms to be linear so that we can write it in a form of an equation. So now we have turned this angular velocity into linear velocity with the help of this term. And again, this is the velocity of the rotor. That is the linear velocity of this rotor that we computed from this equation. So now we can write an equation for our v theta, W2, and u. Because these three are linked up. This is the absolute velocity of my fluid. This is the relative velocity of my fluid, and this is the velocity of my rotor. So because the fluid velocity is dependent upon the velocity of the rotor, and it is moving, so we also have to apply certain reference points for these velocities. And again, if I may repeat, for absolute velocity, our reference point was somewhere outside this control volume that was used to fix this control volume. And in case of relative velocity W2, our reference point was our control surfaces through which this fluid was coming out. And in case of that is the velocity of our rotor, our angular velocity, we computed linear velocity with the help of this equation. So I can write an equation now to make a sense of these terms, and that equation will be used when we solve our problems further in this lecture. So if the velocity of the fluid that is coming out, the absolute velocity v theta 2 and the velocity of the rotor are in opposite direction, means that the velocity that is coming out of this fluid, its direction is this, but the rotor is moving in this direction. So what will be the equation? We will have an equation of v theta 2 is equal to W2 minus u. That is, my absolute velocity will be equal to my relative velocity minus the velocity of the rotor. And if the rotor and the absolute velocity are in the same direction, let's suppose, which is not in this case, but let's suppose that we have the same linear velocity of the rotor, it has the same direction as the absolute velocity. So we will have an equation v theta 2 is equal to my relative velocity plus my velocity of the rotor. So these are the two equations that will be used further to compute the velocities and differentiate between them. So this equation will be used when the absolute velocity and velocity of the rotor has the same direction, the opposite direction, when the velocity direction of the fluid and that of the rotor are in opposite direction, and that is for the same direction when the velocity of the fluid, the absolute velocity of the fluid and the velocity of the rotor are in the same direction. Then a plus sign will be used, and when they are in opposite direction, a minus sign will be used. So this is why I use this scenario to see the different type of velocities that I will have in every rotary equipment scenario. They can change based on the rotary equipment, but now this is pretty much standard that we are going to use for in our lecture. And let's move forward and write some equations in terms of our Reynolds transport theorem, that how those equations will look like. And again, this is a steady state flow problem, so the changes that are occurring inside the control volume due to the momentum will be equated to 0. I hope you have noted this down. Now let's see this equation, that is for my control surface, that is the term in the Reynolds transport theorem for my control surface, that is my momentum, that is my velocity, and that is my mass. So this is R cross V and m dot, that is rho V and A, that is my mass flow rate, and this is my velocity. So mass flow rate into velocity will give me the momentum that is being generated by certain mass flowing in and out of the system, multiply by this momentum. So I will get a moment of momentum equated to this term. So if my tangential velocity is v theta 2 in this case, which is my absolute velocity, I will get this term like this, that is minus r2 v theta 2 plus m dot. So this is let's look at the minus and the plus signs. This is for rotation that is occurring clockwise, and if you can see this will move in clockwise direction. This v theta 2, this v theta 2, its direction is like this, and the perpendicular direction from that axis is r, and that is v theta 2. So the moment that will generate will be clockwise. This velocity will generate a moment that will be clockwise. So that is why we have a negative sign here, and this is the mass that is coming out of the system. So the plus sign is used for the mass flow rate coming out of the system. So these plus and minus signs, whenever you encounter them, they will always show the directional sense of a certain motion or a certain quantity of fluid going in and out. So don't worry about them. This is what the right hand side, in this case, this term of my equation will look like. That will be equal to the shaft torque, that is the shaft torque, and that is the resistive torque that we have to overcome to rotate this sprinkler. So this is what will be, this shaft torque will be overcome by these components of my velocity and mass flow rate and this distance r. So these components in this equation will overcome this shaft torque to rotate this sprinkler. So this is what we are trying to prove so far. And this is how my final Bernoulli, my final equation for this scenario will look like. That is minus R2 V theta 2 m dot, and this whole is equal to the shaft of this, the torque shaft in this case. And remember that we will, if we are taking the angular velocity of our sprinkler in this scenario, that let's say we are given a value of omega, let's say 500 rpm, a certain value is given for our angular velocity, then we will need to compute our v theta 2 from the equation that we used, that is w plus minus, sorry, that is v theta 2 is equal to w plus minus u, that is v theta is equal to w plus minus u. So this is my absolute velocity, and that absolute velocity is equal to the relative velocity of the fluid plus the linear velocity of my rotor. So again, if we are given the angular velocity of the rotor, then we will use this equation to compute our v theta, or even if we are required to compute this relative velocity or the velocity of this rotor. So this is how we are going to use them further down in our lecture when we are solving a particular problem. So let's move forward and let's see if we can calculate the work that should be done to overcome this torque. So let's see this in the next slide. Now we know that what torque is equivalent to when we applied a certain scenario to our Reynolds transport theorem, and we equated this equation, that is, if I might write it, we derived this, that is the torque shaft is equal to my R2 V theta 2 and m dot. Okay, this is what I derived in the previous slide. But I can also calculate my power that is required to rotate a certain shaft by just multiplying it with the angular velocity omega. The left hand and the right hand side, if multiplied with angular velocity, if torque is multiplied by angular velocity, that this will give me the power that is required to rotate a certain shaft. So this is what I have done here. I have multiplied the right hand side and the left hand side of my Reynolds transport theorem with angular velocity, and what I am getting now is power. So power is equal to angular velocity times torque. So we can also find our power that is required to rotate a certain shaft, and if we want to write our equation, that is our Reynolds transport theorem for the fluid that is going in and the fluid that is going out, these are actually the integral term for our control surfaces, but we have written it like this in terms of mass flow rate, in terms of the momentum that is getting in, then the mass flow rate and the momentum that is being generated by this fluid by going out of the control system or the control surface, and the overall power that it will generate. So if you can remember that we wrote an equation for representing our angular velocity as linear velocity, we wrote as u is equal to r omega. So you can see the r omega terms here and the r omega terms here. So that's what we are going to replace these terms with. We are going to replace them with u in and u out. And what we are going to do next is we are going to consider that this is overall a mass conservation problem, that is the m dot in is equal to m dot out and is equal to m dot. So this is overall my mass conservation problem. I am considering that overall my mass is conserved. So m dot will come out to be like this. We will get we can take this term common and divide the power with mass flow rate. So when we do this, we get an equation for the work that is required to rotate a certain shaft. So this is what we get when we divide power with mass flow rate. So we get work. If you remember, power is actually the rate of doing work. So to find work, you just divide the power, that is the power term, the shaft power divided by the mass flow rate. And this is what we get by doing this little math. We get an equation for our work that needs to be done on this shaft to rotate it, and these are the other terms. So this is again, if the velocities are in the same direction, we are going to put this plus sign. If it is not in the same direction, then we do put the minus sign. This is for the fluid going in. So for fluid going in, we use minus sign, and this is for fluid going out, we use plus sign. And again, these plus minus signs are representing the direction of u out and v theta out, because this is the absolute velocity, this is the velocity of the rotor. If their direction is the same, then we will use the plus sign. If the direction is not the same, we will use the negative sign, and so also in this case. So this is what we can do with this equation. Now that with the help of our moment of momentum equation, we can also find the power that is needed to rotate a certain machinery and the work that needs to be done to rotate a certain machinery. So that is the work done on the shaft. So now let's move on to a problem and solve a problem by using these concepts that we have gone through and see what we can find. Now let's look at this problem. This is the same scenario that for which we derived a torque equation from our Reynolds transport theorem. So now let's put some values in those equations and solve it. So the statement is water enters a rotating lawn sprinkler through its base at steady rate of 16 gallons per minute. So this is our volumetric flow rate, that is 16 gallons per minute, and this is where the water is entering from. And the exit cross-sectional area of two nozzles is 0.04 inches. This is the exit cross-sectional area of these two nozzles. These are the two nozzles, and its exit cross-sectional area is given as such. And the flow leaving each nozzle is tangential, that is tangent to this control volume, as you can see with this direction. The radius for the axis of rotation to the center line of each nozzle is 8 inches. Our radius is given, that is 8 inches. Now we have three scenarios in this problem. Number A is determine the resisting torque required to hold the sprinkler head stationary. So for the first scenario, we have to consider that our sprinkler is not rotating, it is stationary, and that will be our assumption that it is stationary, and find the torque that is required to hold this sprinkler head stationary. So what will be this torque? We had an equation. Let's see the diagram for this situation. So this will be the diagram for this situation, in which we are not taking the angular velocity of this sprinkler. We are only taking the velocities of the water, the absolute velocity of the water that is coming out of the sprinkler nozzle. So to write the equation for the shaft torque, we have T, torque of the shaft, is equal to m dot, that is the mass flow rate, that is the mass coming out of the system, that is the radius r, r2 in that case, and v theta 2. We can also write this equation in terms of volumetric flow rate, because we are giving a flow rate of Q is equal to 16 gallons per minute. So to utilize this value, we are going to write this equation in terms of volumetric flow rate, that is the rho Q R2 and V theta 2. So we can put the density of water. We are given the volumetric flow rate when we know the radius, that is 8 inches. What we need to find is the velocity, the tangential velocity. So if I assume this to be a mass conservation problem, and then I can say that the volumetric flow in is equal to the volumetric flow out, and they are both equal to the volumetric flow. So this is basically my rho m dot 1 in is equal to rho, or let's write it more clear. This is equal to rho m dot in is equal to rho m dot out is equal to rho m dot. Basically, I'm assuming that the mass flow rate into the system is equal to the mass flow rate out of the system, and this is equal to the overall mass flow rate. So this is my mass conservation assumption that I'm going to apply for this equation to find my velocity. How I'm going to do this is what I will write an equation for. So if I apply the volumetric flow rate on the nozzles, so how will it look like if I say that the flow, that is the flow out of the nozzle, I have the area. So what I can do is I can take the Q and write an equation for these two exits. So I will name these section 1, 1. These are my control surfaces of the nozzle exit area. I will name them 1, 1. So I have to write the volumetric flow rate for both these nozzles. So that will be A1 V1 plus A1 V1, because the area of this nozzle is not changing and the velocities through that nozzle will be the same, but I have to write two terms for these two separate nozzles. So what I will get is 2 A1 V1. The nozzle exit area is known to me. I know the volumetric flow rate, so I can find my velocity, which in this case will be V theta 2 if we use this notation. So V theta 2 is equal to Q divided by 2A1. So by solving this and by converting the units, you have to convert the units as well. You have to convert this into, like the volumetric flow rate, you have to convert this into cubic feet per second. You have to do this first, and the area is in inches square, so convert this area into square feet and then put it in this equation. So you will get your velocity in terms of feet per second, and that velocity will come out to be 29 feet per second. So now we can use this equation to find the resisting torque that is required to hold this sprinkler stationary. So let's put some values in our first equation and see what we get, what our torque will be. The resistive torque that is required to hold this sprinkler head stationary. So after you will have to be careful that about the units, that you also have to write the radius in terms of feet, the velocity in feet per second, the volumetric flow rate in cubic feet per second, and the density is, that will be in terms of we are using mass per unit volume is cubic feet. So this is what, or you can use pound mass as well. I will suggest pound mass for density, that is mass per unit volume. So that is pound mass per cubic feet. For volumetric flow we have cubic feet per second. For radius we will convert this to feet, and for velocity we will get this in already feet per second. So by putting values in this above equation, we can get our resisting torque to be, that is 2.96 feet and pounds. So that is our torque that is required to hold this sprinkle head stationary. This is our part A. This is our solution for part A. Now moving on to part B, what we need to do is to now compensate the velocity of the rotor in this equation as well. And we know just the term because we have a lengthy discussion about different type of velocities that can occur in this scenario. So we will use that scenario, and for this particular case we will use this diagram. So now we are taking the velocity of the sprinkler as well, and what we need to do is to determine the resisting torque now associated with the sprinkler rotating with a constant speed of 500 revolutions per minute. So again we will use the same equation, that is the shaft torque. Remember, this is the equation that we derived for the sprinkler. So I am not using the whole moment of momentum equation for the Reynolds transport theorem and simplifying that again, because we've already done that in the previous slide. So that's why I'm writing this equation straight away. So this is equal to my rho q r2. Now this velocity v theta 2, now that the sprinkler is also moving and the velocity of the water that is exiting is in this direction and the sprinkler velocity is in this direction, so they are in opposite direction. So now we need to write equation for v theta 2, and v theta 2 will be in terms of w minus u2. This w is now the relative velocity with respect to this control surface. This is the control surface, these are the control surfaces, and this is my relative velocity w2, if I may write it w2, and u2 is the linear velocity of this rotor. I can compute this with an equation that is given here, that u2 is equal to r2 omega. So I can find u2 and I know w2. Remember that when in this case, in this previous case, when our sprinkler head was stationary, so our v theta 2 was actually equal to w2, that my absolute velocity was equal to my relative velocity. So now the sprinkler head in this case is also moving, so in this case now my absolute velocity v theta 2 is equal to w2 minus u2, but I will put the same value for w2 as I derived for the previous section, that was v theta 2 was 29 feet per second for this equation which I found out. So I will use the same 29 feet per second, that was my absolute velocity in previous section, for this w2, that is the relative velocity. So 29 feet per second minus r2 omega, which is this term, and now I can get my absolute velocity v theta 2 in terms of these. So I know that my relative velocity in this case is 29 feet per second minus this velocity, that is the linear velocity of the rotor. So I know r2, I know omega, and it will turns out to be a certain value. So in this case my v theta 2 will be a certain value. I will get 18 feet per second. So now I can put this v theta 2 in this equation right here and solve this as well. Actually this whole term is equal to v theta 2. This whole term is equal to v theta 2 because we can see that. So we will find our v theta 2 now like this. When the sprinkler head is also moving, we'll put the values again, the same values that we used in the previous section, and find our resisting torque now when actually the sprinkler head is also moving with certain angular velocity that was given in terms of revolution per minute, 500 revolution per minutes. So now our torque for our shaft will be a certain value of 1.35 foot-pound. So this is my answer for section B. So this is how it will look like, the shaft torque now when we are actually compensating the angular velocity of the shaft of the sprinkler as well. As you can see, the shaft torque has now reduced when we put the angular velocity of the sprinkler as well, as was in this case it was 2.96 foot-pound and now it is 1.35 foot-pound. So it has been reduced. So now moving on to our third portion of this problem, that is determine the angular velocity of the sprinkler if no resisting torque is applied. So in this case we are going to put 0 in for the shaft torque and multiply our other terms with each other to see what we get. So I hope you have noted this down. So we will use the same equation, but now the left hand side of this equation will be equated to 0. That is the shaft torque is equal to density, volumetric flow rate, radius and v theta 2. So here now this will be 0 and our other terms will be density, volumetric flow rate, radius, and determine the angular velocity of the sprinkler if no resisting torque is applied. So actually we are now going to measure the angular velocity omega, and we can write this v theta 2 in terms of w minus u, as you remember, and we can further write it as rho q r2, and that will be in terms of w minus r omega or r2 omega. So the term that I don't know in this equation is this omega, because this is what is required from us to find when the shaft torque is 0. That what will be this omega. So I know the other terms. The other terms are my density, volumetric flow rate, R2. I can multiply both sides of this equation with these two, with this term, that is my density, volumetric flow rate, R2, and dividing this term by this term, this equation by this term, that is this term, I will get 0. I will get an equation 0 is equal to W minus R2 omega, because this term will cancel out. So now I can solve this equation further. Just write it here. That is 0 is equal to W minus R2 omega. W will be again the velocity, that is 29 feet per second. R2 is 8, and what we need to do is to find omega. So this equation will look like now this, that omega is equal to W divided by R2, which will be comes out to be my rotational velocity for the sprinkler, that is 96.3 radians per second. So this will be my angular velocity for the sprinkler when the shaft torque is equal to 0. So this is my third part C for this problem. You can also convert this radian per second into revolution per minutes by multiplying and dividing it by 60 and dividing it by 2 pi radian. So you can also convert this into revolution per minute. Revolution per minute. So be smart about the unit conversion, because this is what determines your whole equations and your final answer. So please go through your unit conversion, practice it, because we will need it a lot in the future also. I would like to point out that there is a same example of this nature. This was a problem from your Munson book. There was the same example that is being solved in your book, in your Munson book, just in the moment of momentum portion. So go through it. It's the same example, just the units are changed. So go through it, go through its theory, so you can comprehend the moment of momentum portion a little bit well. Thank you. Hafiz.